but have not submitted them, this is the format for the algorithms. And this is for an algorithm for simply getting the food for the party. It does not have the constructs that we want. Can we go back one slide, Ketley? There's actually a remote control, which I don't have with me, but I'll back one slide, just up arrow. One more time. Up arrow. Bottom line, up arrow. Not responding? Could it be the cursor is not? Okay. Let me see what arrow you're pressing. No, not the arrow. Down here, bottom line. That's down and go up. Okay, hold on. Go back one. Back one. Back one. Back one more. That's it. Okay. So this algorithm does show the constructs that we're looking for. We have the do while, which is the repetition or looping. In this case, we're doing while names remain in the address book. We have the branching or selection here with the if the student is at home, or if the person is at home, then do this, else do that. And we see the sequence construct. Yours should be done just the same way with the proper indentation. Don't require the underlining of the verbs that begin them, but you should put yours together much like this. Any questions? Yes, sir.
Does every line have a beginning, like if the verb has to be like the first word of the sentence?
I would like it to be that way. We're writing in what's called pseudocode. It's not a very formal language, but it does have some structure. So try to phrase these yours in similar ways to what I have them done here. Can I get 2 slides up forward? Kelly. So remember our decomposition. And can you go one more slide? And again. And again. 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 Our 4 constructs again. I think you may be going backwards. You're going backwards instead of forward. One more time. There we go. Okay. So here's our decomposed problem with our, anybody remember what I call these data elements on the arrows? Starts with a P. Boy, you guys are glad I didn't give a quiz today. But parameters. Anybody remember also what parameters are used for? Take a look at these guys and it might just be common sense. What does finding a place for the party need as initial data to get started? Dates and times. And once it's complete, what does it produce? A particular place and date and a particular time for the party. Okay? So if these parameters that are part of the incoming arrows are called input parameters. And if you look at the record music, I don't have any on the structure chart. But you will and need to make up some input information that's necessary for recording music. And just again gives you a start. Can anybody give us perhaps some ideas of what might be the necessary information that someone would need to start recording music? Yes? The length of the party would be a very good idea. And just to elaborate on that just for a minute, the length of the party would have something to do with the repetition of recording, right? You might want to record until you have reached the time limit. Maybe go over half hour. Okay? I had another hand here for some other inputs.
Oh, the genre preference of your guest.
Very good. That's another one. Yes, sir.
Maybe you could charge by the hour cost.
Oh, you're saying if I'm recording the music from a group, I might have a charge per hour?
I'm saying like maybe they like how they maybe charge by the hour. Say like the party a certain amount of time, what's the cost?
I think that's what the young lady was saying here. The time or the length of it. Yes. Somebody, you're right. I may have a different recording device or a playback device at my home, and I want you to use the same one for your recording. Yeah, good idea. All of these are possibles. Nobody should have identical algorithms. Okay? So just to give you the beginning of some way to thought. Any other questions about the homework? Yes.
How long should the algorithm be? Like how many steps?
Can you go back one from here? About 8 steps. 1 page. I mean, I've seen 3 pages with 37 steps so far, and that's not bad. That's a little overkill for right now. There's got to be a key question that someone's going to ask about this homework.
So we have the algorithms and we have the possible inputs and outputs? Or we just...
Good question. 1 second. The inputs are described in the first step. Remember our structure chart? Those are the input parameters. Look at step 8. What's that? The output parameter. Okay? These are pieces of data that come into the process, used and are processed, and modified, and then come out. Input, process, output. That's the structure of your algorithm. Okay?
But this is the output for get the food. Oh no, that was
yeah, that was a whole nother spot. But if you go back to my algorithm in the slides, you'll notice that these step 1 and step 8 match the input and output parameters on the structure chart. The key question is, Professor Keelan, when can I turn this in? I haven't done it yet. What's the latest I can turn it in? You got to turn it in by the end of today because it's due today. Okay, so I will have email from everybody by the end of the day.
You send it to the same email you send to the lab.
Yes, but as Ketley's indicated here, everybody's met Ketley and Andy. If you haven't, you will. Subject, assignment type, the number. This is assignment number 1. Your ID, your last name.
So your algorithm should say PROG 1, comma, your HUID, and your last name.
And the reason we do this is because last semester we had 1,200, and we had a smaller class, 1,200 emails by the time we ended the semester. And that's a lot to kind of get together, sort, and organize, and everybody needs to identify their email because we don't want you not to get the grade you deserve. Any other questions before I move on? Yes, sir.
Can we still turn in the paper version of it, or how do you do it?
I prefer you not turn in the paper version. I prefer you save a tree. All right, yes.
Can we alter? I sent my emails, but can we alter it? If we
Yes, you can. How would you like that? With the revised
yeah, I'll put like
in parentheses?
disregard last from.
Okay, but here, to help us identify it, we want you to give it the same subject that you gave the previous one, and at the end of it, put revised. Okay? More questions? Let's move on then. Okay, can we move on to one more, two more, keep going. I got about 5 slides I've already gone through. Keep going. One more. Right there. Go back one. Right there. And in the future, guys, I do have a little, so I won't have to have you do this. I have something I can use for remote control. Okay, so we were talking about the broader engineering process for developing systems. And you'll notice that oftentimes I'll talk about developing systems, and then sometimes I'll talk about developing software. Okay? I want to pretty much use those things as synonymous. Let me tell you why. Okay? Because if you think about an information system, and I have some interesting stories to tell, and I don't have quite time to do it right now, but a system is made up of many components. Software, or what we consider the programs that we will develop this semester, is just a part of that. Okay? One of the key components of systems are the people that are involved in the system's operation. A key part of a system is the hardware, and you will have hardware courses, I'm sure, for those computer engineers as well as those systems and computer science majors will all have hardware. And we will have the documentation, training, and other softer aspects, and so I consider that all the system. And what we're going to talk about here in the first few classes, and what's described in some part in your chapter 1 in your book, is the systems engineering process. And the previous phase was called the problem definition. the analysis phase, where we take a look at the problem, ask key questions of how long it's been there, is it reoccurring, do some cost-benefit analysis. I'm going over a little bit of my previous slides to catch us up with where we are today. This is the second phase, the implementation phase, and now we have selected a solution as a result of our analysis in the first phase. We have, in a more broader sense than is outlined here in this slide, we have constructed designs, both broad and detailed, and constructed one of those solutions, and now we're actually implementing our solution. So in a more of a business standpoint, I'm a user, I call in my information specialist, I tell them what my problem is. That's my analysis phase for me, the client. Then they go back and further the analysis phase by developing several solutions for me, coming back and saying, well, I can do this, this, or this, which one would you like? This one will cost you $50,000, this one will cost you $55,000, this one will cost you $100,000. We choose a solution, I go back to my office as an information specialist, I design the solution, I detail it out, I give it to my groups, I decompose it into different component parts, and I execute it and get it done. Now we're implementing it here. We're sending it back out to the client's office. Now let's get it operating in your environment. And I should tell a little bit, I should slow down a little bit because I want to make sure you understand this process. This is a very innate process that we typically do in various ways for all kinds of problems that we solve. And in a more academic sense, it is the engineering approach that you're going to see in many other courses, engineering courses here. It is a approach that one uses to construct anything of some moderate complexity, like this building here. This building that we're in, or this university in general, was not begun with step 1, step 2, step 3, put a brick here, put some mortar on it, put another brick on it, dig a hole, no. It was engineered, it was well thought out, it was planned. Several alternatives were suggested. Those alternatives were evaluated. One of those alternatives were selected, and more detailed planning took place from that point forward, where actually the dimensions of this auditorium and the height of its ceilings and where the electrical plugs, as few as they are going to be placed, that kind of detail was developed. And then various contractors were brought in. The problem was decomposed. There were certain contingencies between the various subtasks. Those subtasks required inputs and outputs, and some required outputs from previous ones. For example, the plumbing in this room, okay, was very much dependent upon the architectural design of this building. So the architect's planning had to take place before the plumbers could come in and say, now we'll put a pipe in this wall and we'll put the electrical fixtures here and there. So things are very dependent upon one another. I need you to, thank you. I'll try to stay in one place. So here we see, okay, more relevant description of the implementation phase to what you're going to be doing in this class. But I always want to keep you mindful of the fact that we're just taking a very narrow view of what is a more broader methodology of engineering systems. So here we're testing our programs. We are producing errors that we will then correct, and that will be debugging. Fixing those errors, you'll know these terms because you'll experience this process on a weekly basis of writing code and debugging it. I'm sure all of you who came to the lab on Tuesday had some errors in what they typed, and when they first compiled there were some error messages. So that debugging process is somewhat familiar to you. So let's talk a little bit about testing for the moment, because this is one of the areas of my research. Testing is not simply, let's run through the program a few times. Let's run through it a few times, and if it looks like it works, let's deliver it to the client, okay? One of the things that we're going to do in this class is a very formal approach to testing our software, okay? How does the process begin? It begins with you reading the assignment on the web, and the first deliverable that you're going to give to me is going to be an algorithm written in pseudocode, okay? And the second thing, part of that first deliverable, is going to be what I'm calling a test oracle, where you will actually, with paper and pen, crunch some numbers, which I will give you in some cases. In some cases you will make up your own. In some cases it will be both your numbers and my numbers. And you will crunch through the algorithm and put these numbers in many cases into formulas that produce results. We saw those slides in regard to a particular topic or a problem that was a payroll calculation for someone's $14.75 hourly rate and for 52 hours having worked. That's the kind of numbers that you'll crunch through the algorithm. And then you'll come up with a result. I think it was $1,400 or some odd for the weekly payroll, bi-weekly payroll for this person. That test oracle and the algorithm will be turned into me on Wednesday. And then on Friday, you will use your copy of that test oracle to tell you what the evaluation criteria is for your program to be working, and so it will be the basis of your testing output. Now, I need to make this clear. It'll become clear because we'll do it at least 10 times this semester. So you get a problem, you write an algorithm, you run some numbers through the algorithm on paper, you show the results. You keep a copy, you send me a copy. When you write your code and you put these same numbers into your program, you would expect the numbers that you put together in your hand calculation to come out as the result of the program being running. If the program is a reflection of your algorithm, if it's just another translation of your algorithm in machine language, in machine code for the computer to understand, then it should come up with the same numbers. Everybody understand what I'm asking you to do? It establishes that when you run a number through a formula and it comes out with a result, $1,475 in our previous slide, okay? And you run a program that supposedly takes the same numbers in and does the same process that your algorithm performed on those numbers, the result should be the same. So your testing is to make sure that it produces the correct results. How do we know what the correct results are? We've hand computed these results, and now if my, for example, payroll program produces the same results that I've done on paper, then I can be fairly assured, with perhaps a little more testing, that it's going to produce the outputs for many other employees who have different biweekly pay rates and have different hourly performance over a bi-weekly period. Take a look at the slides, read chapter 1. I think some of this will be clear. I'm not going to take too much more time on this, but I will allude to this process as we go on with other slides. Can I go to the next slide? So our maintenance phase is where we've delivered our clients the product, they're using it, and we will from time to time modify this system to meet our needs, but more often than not, since someone is using this system, it cannot always be modified adequately to solve the problems that occur. And if you think about some systems that we have here at Howard, let's see if I can come up with one. Oh, everybody's registered, right? Everybody's registered using our online system. And has anyone come up with any errors? Anybody see any flaws in the system? No? 60 people have used we've got a great system then, yes.
When we were taking our placement exams, it would give us an error message saying that they didn't got our scores, and I actually had to go over to the main office for them to change it.
That's a problem. Now, it's probably very difficult for them to fix that problem, but the next time you register, you would hope that that error should not come up again. So someone has used the system, and hopefully it's being modified. And the way our system works is that you can put rules in it to make it modifiable on the run while it's still active, to make it change its behavior by putting new rules in. So that's a nice design. But it's what we're talking about here, where we talk about correcting errors that show up in the maintenance, okay? But more often than not, you can't make these changes unless you put out a new version of the system, or you take the system down, rewrite some portion of the software, go through some plugging of it into some testing data, and then run again. This is the cycle that we're talking about. The cycle, as we explained, I guess last week, repeats itself and is a self-perfecting loop. So a piece of software will get installed initially, like when we first started with this Bison Web registration system. It had some bugs in it. So we reported those bugs back to the manufacturer. they sent us some bug fixes. We applied those bug fixes the next semester, did a little bit better, applied some more bug fixes, and so forth. The cycle of problem analysis, maintenance, testing, implementation, testing continues until the product is sort of been debugged and modified to death, and then we throw it out and come up with a brand new design that sort of addresses some new extra. Yes?
I mean, I guess it's kind of stupid to ask, but is there any way that you can like minimize those problems from the get-go without going through all those loops? Like if they would have sent the Bison Web and like sent all the bug fixes or whatever right away, like
well,
what caused the bugs along?
Sure. We see that happening on our computers all the time. Many of you own PCs, majority of you own PCs. And you know that from time to time, Microsoft, if that's the operating system you use, or Apple, will send down updates. And these are automatic updates, and a little thing that says, this update's ready for your computer. These are the results of bugs that somebody has reported back to Microsoft. You may also see from time to time, it'll ask you about, do you want to send this bug message or this error message back to Microsoft? And most of the time you say, don't send, okay? But there are people who send it back, and there's some people there that are looking at these bugs, and they say, oh man, we forgot about that, let's go fix it. They put out an update, and that update comes down in a week or two into your computer, and it all happens without you having to do anything but just click pointing. So there are some bugs though in systems like the Microsoft operating system and our Banner or our Bison web system that we do our registration with here that can't be fixed like that. Very significant flaws that require us coming and doing a new version of the software and having that installed again before the next registration period. So yes, there are mechanisms for fixing it on the fly, but there are certain classification of errors that cannot be fixed in that way. Okay? Can I get the next slide? Okay. So here we see our programming lifecycle, or our systems development lifecycle as I refer to it, broken down into a little more detail. Analysis and specification, general solution or algorithm, and this should say solutions because oftentimes we produce at least 3 possible solutions to the problem, evaluating the best one, and then moving on to the 3rd verification phase, and that's when you run some numbers through your algorithm to make sure it works. Then we have a implementation phase where we develop our concrete solution. That's where programs are developed. We test those programs, we put them into the maintenance phase, and we begin to use them, and the bug fixing, or at least the changes that can be made during the execution or maintenance cycle take place here. And then when we have continually done this for a period of time, oftentimes this is it's called post-implementation review. It's done here in maintenance, and we say, hey, we've got enough fixes now, let's go ahead and put a new version out. Let's start our cycle back over again. Let's analyze and specify solutions to those errors that we've gotten from our users. Let's come up with a general solution, let's verify them, and let's keep the cycle going, and it perfects itself over the life of the system. Right? It's called the life cycle. Can you go one more time? Now, switching hats for just a moment. Okay. What you're going to try to do, many of you, is to give me an algorithm on Wednesday and then come in on Thursday or whenever to do your coding and try to just code. Debug, code, debug, code, debug, code, debug, code, debug, code, debug. And hopefully, though we can't see it here, you have a finished product. But you notice, as this slide illustrates, that's a fairly long path. Okay? This path at the bottom where you think about the solution is what I'm going to ask you, and actually not ask you, I'm going to force you to follow. This requires that you go through the algorithm development, the test oracle, application to the algorithm, and then that gets submitted before you actually go and start your coding. And even more so, I'm going to ask you to do this. I'm going to ask you to tie in your pseudocode into your source code. For those of you who have read chapter 1, you know what I'm talking about. If those of you who don't know what I'm talking about, you need to read chapter 1. But I've got my pseudocode algorithm that I've prepared for Wednesday's submission, and I'm writing my source code for Friday's submission. I'm going to ask you to take the pseudocode that corresponds to the instruction in the source code and copy it from your algorithm into a comment in your source code. So what I'm going to see is I'm going to see a program that is the interpretation of your I shouldn't say interpretation. I'll say translation. Interpretation is a different term. Translation of your algorithm into C++, but those statements in C++ will have comments that include your algorithm. Try it. You'll see what I mean. Can I get the next slide? So, question? Okay. Let me see if I can sum this up in about 10 minutes. Our book discusses a coding system called binary. And when we hear in other regards, not only in the information systems or computer industry, the word digital information, we're talking about binary coding of information. Now, we will no longer, after the end of this year, have free TV. Everybody's aware of that, right? Well, what they're saying is that we will be going digital. Hurrah, hurrah, hurrah. What they're not telling you is that no more free TV. Okay? And guess what? This few years down the line, there'll be no free radio either. It'll be all satellite and such. So, what are we talking about here? What are we talking about here? Right now, when you have a TV that has, the rabbit ears on it, okay, you're getting an analog signal from a broadcast tower somewhere in the area. That broadcast tower is producing an analog signal, which is, I could talk about analog signals, but it's a sine wave. Certain amplitude and amplitude changes the way in which the screen reflects color, and also sound is carried upon this wave. Okay? That's analog signals. That's why you get, I don't know if anybody has these TVs in their house anymore, but you get a little fuzziness and a little running and things like that on the screen, because those signals are not very secure, they're not very clear, and your TV set doesn't interpret bad data very well. When you go to digital information that's coded in bytes of series of ones and zeros, the data is very, very accurate, and where you'll see binary information now is in CDs. If you play a CD over and over and over again, the sound should not degrade, okay? Unless you scratch it or break it or whatever. Because the digital information that's recorded on that CD doesn't change after it's been played 100,000, a million times. But if you had a cassette, I don't know if anybody ever seen one, but they still exist. A cassette, which is an analog recording device on a piece of magnetic tape, okay? After you play it so many times, the magnetism gets lost and the clarity of the information gets garbled, and errors get in, and the music gets garbled. So you play it about 20,000 times, a lot, and it's not going to play very well. So the reason we're going to digital and binary coding of information is because the data lasts longer and is not degradable. Okay? So, as you would expect, this has some relevance to our topic. In our computer, all the information is digital. All the information, programs, data, even the sound, the music, the animation that you see on the screen is all coded and represented in numbers of ones and zeros. And those ones and zeros are grouped in sets of 8 called a byte. And we see measures of these bytes in kilobytes, or 1024 bytes is a kilobyte, and 1 megabyte. So now we're talking about other larger sizes of data. And what might some of those be? What's the next increment up from a megabyte? A gigabyte. What's the next measurement up from a gigabyte? Terabyte. Okay? So, yes?
If you use like a video card and connects like analog signal into the computer, what will be?
A video card.
Yes, if you connect if it's receiving analog signals, what is the computer processing?
I don't know what the name of the process is, but it's done very rarely. What you're saying is that you have an analog signal coming into some device, and that device changes that analog signal into a digital signal.
Is that what is happening?
Well, no, I gotta say, it happens, but it happens rarely. I'm trying to figure out a time when it happens. It may happen in some TV sets. that take in video from an analog signal but display the picture in a digital way. Did you have a question? I'm sorry.
Yeah, is that what they mean when they say digitally remastered?
Yes. Okay. Good. That's a good example. I think she's giving me a way of answering your question. An old movie, okay? An old movie that used to be shown in theaters on a big, projector, and the light comes out, so it's on. That is on a big piece of tape. That's an analog. Okay. Now they want movies that have been digitally. What was the word you used? Remastered. So let's talk about for a second what that means. That means that there's been a device that reads in that analog tape and puts it into ones and zeros. Okay? But because that tape has been played many, many times, it's got bad spots on it. Have you ever seen an old movie that's got little spots and little things in it and so forth? So how do we get rid of those? Well, there are algorithms that take the input, the ones and zeros that represent that old garbled old movie, and changes some of the ones and zeros with some algorithm to make it more clear. So, for example, best example that I use here is, let's say that you got a black and white old movie and it's being colorized, okay? Being colorized. And you imagine, how in the world would you colorize a black and white movie? It's grays and whites and blacks, okay? But there's certain grays represented in certain sets of ones and zeros that correspond to green, and certain other little modest changes in that ones and zero pattern that correspond to light green. And so everybody's familiar with what a pixel is, right? A pixel. And on our TV screens, we have, hundreds of thousands, millions of pixels. Each one of those pixels is a particular color. And by making that particular pixel represented by 1 byte or 3 or 8 bits of ones and zeros, we can make a black and white pixel into a color pixel. And in fact, this has been done for years. You can take a black and white movie and run it through these algorithms, and you can come up with a color movie. Not exactly, it doesn't look that sharp, but it is color. Okay? And we're finding that more and more of the information that used to be represented in an analog way is now going to be represented in a digital way, and it preserves it. Okay? You don't need to know this to program computers, but it's a good thing to know as you understand how the information technology that we are encountering in many regards on the internet and in our appliances and our schools and our jobs and our cars, even in traffic and weather outside as we monitor our environment, are being represented in a digital way. And if it can be represented in a digital way, it can be read by a computer program and modified. That's why one of the nice things, everybody's seen the approach to some of these basketball games, Xbox and games, where the let's say Dwayne Wade is wearing a black suit, and on the black suit there are lights, right? Light, and there's a camera that's taking pictures of him slam dunk with this black suit with the lights on it, okay? And then it's run through some algorithm in some program that now produces the animated character that makes him look, Dwayne Wade slamming slam dunk. Or there's been many movies. I was asking somebody about Lord of the Rings, and this little character in Lord of the Rings that kind of crawls around on the ground, and that's a real person. It's a real person. Yeah, Smeagol. So that's it. So how in the world? How did they get that? It looks like a human being. It looks like a person. Okay. What did they do? Again, somebody who had some slight build crawled around on the ground with that light suit on. They recorded that light in a digital way. They ran that digital film through an algorithm that cut off the person's, looking like a person, and put on the back of him that little legs things that he's got running around, and now it looks like a real creature running around on the movie screen. Okay? So a lot of different things can be done with information once it's been digitized, and it's an enormous amount of research, and hopefully some of you will get jobs in that industry and make a fortune. Can I get you to go to the next slide? Kathleen, can I get you on the slide, please? So this digital information is a way of representing very simple pieces of information, like the number 1. Okay? And in our case, the number 1 is represented in our computer by a binary coding system. So if we were to represent the number 1 in a binary coding system in 1 byte, it is 4 zeros followed by 3 zeros and a 1. This is a binary representation of our decimal number 1. So, how will we represent the number 2? Ah, somebody got it. I think I heard the right answer there. 2 would be equal to
6 zeros.
all right. Now let's tax your mind a little bit more. How would you represent a 3? Okay, now we'll figure this out in a moment, how this works. How will we represent the number 4? 0, 0, 0, 0, 0, 1. Everybody's like, what? What? I'm confused too. Let's bring some clarity to this. These are all correct. Because like a decimal number, our decimal numbers are represented by powers of 10. That's 8 times 10 to the 0th power, or 1, plus 7 times 10 to the 1st power, 4 times 10 to the 2nd power, plus 3 times 10 to the 3rd power. So the place in the number corresponds to the unit position first, the 10th position, the 100th position, the 1000th position. This is decimal, or base 10 numbering system. This is binary, base what? Base 2. So our number 4 here, is 0 times 2 to the 0th power, plus 0 times 2 to the 1st power, and 1 times 2 to the, 2nd power, or 4. Okay? So now we see how 4 is represented. What's happening with 3? 1 times 2 to the 1st, or 2, plus 1 times 2, 2 to the 0, plus 1 times 1, that's 2 plus 1, or 3. Get it? Now, I would be real mean if I put on a quiz, represent the number 57 in binary. All right? Believe me, I would never ask you to do that. But I would expect you to be able to represent the number 3. Do what? 44. 4 is equal to 0, 0, 0, 0, 0, 1, 0, 0. Because that 1 corresponds to the 2 to the 2nd power. 4. Okay? So, how would you represent 8? Two to the 0, 1, 2, 3. Hey, guess what? 2 to the 3rd power is 8. What about 10? Could I represent 10? That would be 2 to the 8. That would be 8 plus 2. Where's the 2? Right here? That's 10. How would I do 11? That's 11. 8 plus 2 plus 1. So what is this? This is 3 times 10 to the squared, 3 to the cube, 10 to the cube, 10 to the squared, 10 to the first power, 10 to the 0th power. It's the same process that we do in our own minds when we read decimal numbers. So we can represent numbers in decimal. But we can also represent letters, special characters, and many, many other things in these bytes as well. We just simply need a coding system. And the coding system that we employ in our PCs is called an ASCII. It's an acronym, and I'm not going to begin to tell you I know what it means, but it's some kind of a standard way of representing a lowercase a in some bytes or an uppercase a in some byte configuration. But when you type these words into a word processor, what's behind the scenes inside the computers are these ones and zeros that are the ASCII representations of those digits.
Are those binary codes the same in all computers?
The binary code is the same, so numbers are represented pretty much the same. But letters are represented in different ways depending upon the different coding system. So you'll read in your chapter about EBCDIC and ASCII. Those are the two major ones. EBCDIC is more European, ASCII is more American. Okay? All right, I'll finish up. Please, folks, shh. Today is Wednesday. I will finish up the slides for chapter 1 on Friday. I did not give you a quiz today, but I did tell you last week that I will give you a quiz every week, so you can make the deduction. You write the algorithm, so you figure it out. Okay. Thank you. Kill it. Hit